All right. So, thanks for coming, everyone. Today, I'm going to talk to you about the past 6 years of cleaning the air filter. Maybe later. So, the title of this talk was kind of comic. Why the weird wings? It's alliterated. This has been the goal of my basically the last 10 years of my curiosity and research, and specifically in the last 6 years here at the University of Montana. So let's talk about feathers. Feathers are the most structurally diverse, phenotypically diverse structures in the vertebrate world, integumentary structures probably. They come in all kinds of different shapes and sizes, colors, even chemical compositions. We've got feathers that have chemical compounds that are unique to certain species of birds. They vary between the species, between sexes, between locations on the body, even within a single feather follicle throughout an animal's lifetime. And perhaps the best way to illustrate the diversity here is to look at the feathers of the tail. Tail feathers are extremely diverse. We've got a diversity of function, everything from the very tiny spine tails and those swifts at the top, which serve a function in perching on vertical surfaces, to aerodynamically normal tails of soaring birds, to sexually selected, weird, elongated wings. And this is not particularly new morphology. This is actually 120 million years old, 130 million years old since the Jurassic. These are the tail feathers of some Jurassic theropod dinosaurs. Tremendous diversity specifically is largely due to the type of visual signals in birds, where we see these have evolved dozens, if not hundreds of times across birds in many different ways. The paradise, as well as this meter-long lyrebird's tail. However, conversely, in the wing, we see sexually selected visual signals have only evolved in 3 species. 2 closely related nightjars and the Argus pheasant. And this is largely because the wings, the feathers of the wings, are required for flight. They are morphologically constrained to perform well during flight. And so most birds possess a morphologically stereotyped feather. That's just very normal. So these are actually P6 feathers from a housefinch and a tundra swan, scaled to be about the same size. And they are remarkably similar in shape. And this isn't something that's just restricted to, I didn't just cherry pick 2 species. We could talk about all types of birds, from warblers to woodpeckers, egrets to eagles, anything. Just about any bird you want will have a morphologically stereotyped wing feather. Even the tiniest flying birds and the hummingbirds, we see morphological stereotyping there as well. And in 120 million year old theropod dinosaurs, even though it's debatable as to whether or not these guys were actually performing powered flight. But they still have this asymmetrical and stereotyped shape. And then that brings us to these oddballs. So like, what is going on here? And this has been the target of my dissertation. It's captured my attention for about 10 years now. Specifically, how do these feathers deviate from this aerodynamically constrained form? If so many birds have this normal shape, this typical feather morphology, what allows these other shapes to occur? So this is the target, the primary question of my dissertation. Why do these feathers deviate from a typical aerodynamically constrained morphology? In other words, why the weird wings? To answer this question, we might start by looking at the feathers of the tail, which have been subject to much more research than the feather shapes of the wing. And in the tail, we see that there are some morphologies, like these elongated streamers, and not quite elongated, but these narrow pointed feathers in swallows and martins are specialized to improve maneuverability during flight. So this is a specialized, can be thought of as a specialized aerodynamic device that improves the maneuverability of in certain swallows. So we might see feather shapes that become specialized for unique types of flight. We might also see feather shapes that become specialized to produce sounds, because these feathers in bee hummingbirds. So we've got these tail feathers in the top Allen's hummingbird here, produces a sound like this during a dive. And then in our Anna's hummingbird on the bottom, we get a sound kind of like this. It's going to be followed with some squeaky vocalizations. And these sounds are called sonations. This is a form of communication, and this is going to be the focus of my first chapter, my dissertation. So sonations are acoustic signals in vertebrates that are produced by structures other than the vocal cords and the syrinx, things external to the body, like the limbs, the head, the tail, hair, feet, etc. It includes things like the shaking of the tail of a rattlesnake and that structure at the end of the rattlesnake's tail. It also includes structures that aren't particularly specialized, like the chest beating of a gorilla. Those are really specialized sounds. And then also some really weird things in birds. So birds specifically have evolved wing or sonations that have evolved sonations that involve wing or tail feathers. Approximately 70 times. They occur in nearly every volant order. You heard the hummingbird already. I'm gonna play it one more time. But we also see these sounds in things like sandpipers. This is a snipe performing a winnowing display. Or in the dive bombing displays of nighthawks. Or in whatever this display is in the Quan. These are all sounds that are produced by feathers in the wings or the tail. They're specifically, because they're produced by feathers, we consider them sonations. So sonations are often associated with both a unique morphology and some unique behaviors like a display. So here in the club-winged manakin, we've got some secondary feathers, feathers in the arm wing that are club-shaped, where it gets its name club-winged manakin. And those weird feathers actually rub together at really, really high speeds to produce a ting sound. Let me show you what that display looks like. Go. No! The computers have been doing this lately. Play. Play. No! Oh, God. Well, the bird does this really weird behavior where it jumps around, and every time it jumps, it actually flips its wings together to create a snapping sound. And then it'll jump and briefly raise its secondaries so that they're making contact with each other and vibrate. It's one of the fastest vertebrate movements in the world. And that vibration actually causes this really high-pitched little ding sound, just like that. Exactly. I should just do this all the time. So we see this weird behavior, the specialized display, as well as a specialized morphology. Similarly, in things like the crested pigeon, we see these birds perform, or they produce some interesting wing sounds when they fly. So here's a spectrogram. This is a way to visualize a sound. We have time here on the x-axis and the frequency or the pitch of the sound on the y-axis. The darkness of certain sounds indicates how loud they are. Vertical bars here are broadband sounds, while the more discrete horizontal dashes are discrete tonal sounds. I'll play the sound for you really quick. This is an alarmed takeoff from a crested pigeon. And it has some whistly elements to it. And it turns out that if we take this modified feather here, which you might not have even noticed is strangely shaped, it is significantly narrower than any of the other feathers in the wing. And if you take that feather and you stick it in a wind tunnel, it'll actually produce a sound at the same tone as those 3,500 kilohertz tones in the flapping bird. So this is a this link between morphology and behavior, we see an interesting sonation that is also associated with some sort of morphology that produces those sounds. So this brings me to my my first study group, the Columbina ground doves, which have this interesting feather shape. I'll actually pass around one of these because we're in a smaller room today. I'm going to pass around a wing, and if you just want to leave it inside this little plastic case, that'd be great. Here you go, Brett. And take a look at these third primary down, the seventh primary, so 10, 9, 8, sorry, 4, 7. The seventh primary is going to have this weird hook shape to it. So I did in a survey of all 8 species in the genus Columbina, I identified a couple different morphologies. This is a genus of small sparrow-sized ground doves that are endemic to the New World. They are fairly closely related, and they're also about 50 million years diverged from other members of the family. So it's a relatively distinct, it's one of 3 distinct families of pigeons and doves. And the majority of the members of this subfamily are in the genus Columbina. We've got 8 species here, and I identified 3 different, more or less different shapes here that vary in the length of barbs in this weird modified region. So here is a close-up of that feather vein where that big protrusion is. And we see that there are barbs, these guys that branch off from the primary shaft of the feather. And those barbs are relatively short, but still elongated in Columbina inca-like feathers. And then in the Talcopodi-like feathers, it's extremely, extremely elongated and creates a really large protrusion. And then I wanted to test these feathers, so I joined up with Chris Clark at UC Riverside and used his fancy pants aeroacoustic wind tunnel to test the function of these feathers. I put a whole wing into the wind tunnel. Oh, this isn't going to play again. All right. So putting a whole wing into the wind tunnel, there's this little protrusion here on P7, and it actually flaps about 260 times a second, and it makes contact with P6 just behind it. And so that flapping and the contact that it makes with the adjacent P6 feather produces a buzzing sound. In flight, these birds also have a pretty buzzy wing sound. I'll play that for you really quick. So that's the wing sound of this common ground dove. I'll play it one more time. It has a very fast wing beat, and notice the weird buzzy quality to those wing beats. So those wing beats are kind of interesting. They've attracted the attention of naturalists for about 100 years. People have been debating them. And it turns out that if you slow down these wing sounds, or if we take a really close look at the spectrograms, we can start to see the actual moments where each of the where that feather collides with the adjacent feather, where this little structure flaps up against P6 on those spectrograms. So I'm going to play a slowed down version of that sound and listen for something that sounds kind of like running a finger across a comb. It's a brr, brr, brr sound. So take a listen. So that's actually those, we can actually start to visualize each of the moments where that feather collides with the adjacent feather, produces a broadband peak. And those peaks occur at about, in living birds, they occur about 300 times a second. This is a pretty good match between morphology, the way that morphology behaves, and the sounds that we've recorded from living birds. So this indicates that this morphology is producing, is adapted to produce those sounds. It's an interesting feather shape that deviates from an aerodynamically stereotyped form in order to produce this weird fuzzy wing sound. Even in the species, those Inca doves that have the shortest of those elongated barbs, these were the ones on the far left initially, even these feathers produce produce buzzes in the wind tunnel. Experimentally silenced using some tape. We covered up every single adjacent pair of feathers with a little bit of tape just to cover that flapping region in order to prevent each feather pair from fluttering. And then we recorded the sounds of those that the wings were making. And it turns out that whenever P7 is allowed to flap, so whenever this guy here is allowed to flap, we see we hear the loudest sounds. If we take both P7 and P6, the sounds are essentially muted. And we no longer hear those buzzes. So this indicates that that feather is indeed producing the wing sounds we hear. So this is a wing sound of the Inca dove, and I'll play it for you. It's going to be 2 flights, and take a listen for those the weird buzzy quality of those sounds. So here, from our analyses of flying birds in the wild, we've identified those peaks that occur about 350 times a second, which is a really strong match to the peaks produced by an individual wing as we watch those feathers flap. So taken together, this is pretty strong evidence that these weird morphologies in the Columbina ground doves are producing sonations. In 2 species here, in the Columbina squamata and Columbina inca, we've done some playback experiments, and there's some evidence to suggest that they're interpreting these sounds as signals of alarm. And then there's also this really interesting guy here. You'll notice he kind of has a different morphology than all the others. This is the most sexually dimorphic of the species. And this is the only species that has ever been reported as producing wing sounds in display flights. And it also is the species that has the largest barbs in its modified region. So there's also a possibility that there's some sexual selection influencing the sound production here as well. So together, this is a good example of how feathers in the wing can be modified to produce sonations in the Columbina ground doves. But what about feather shapes that might be influenced by specializations for certain types of aerodynamic force production? In the tail of the swallows, for example, these elongated regions of the outermost tail feather increase maneuverability in swallows. Feathers of the wing, however, haven't been as extensively studied in terms of how their shape influences their force production. We know for a few cases of how feathers can be specialized for certain types of force production. For example, in the spreading of the wingtips in the soaring condor or in soaring corvids, those spread wingtips, each feather tip generates its own little vortex. And those little vortices then swirl around in this larger vortex, and that spreads out the vorticity along the wingtip, which actually reduces the drag on the bird. And so this behavior is something we see in a lot of birds that soar. We think that it's specialized adaptation for increasing efficiency while soaring. But we also see almost all birds have a pretty large alula, which is the thumb feather on the hand wing. And that feather often gets deployed during slow flight. Oh, this video is not going to play either. It's so pretty. So there's this barn owl coming in to swoop down onto its prey. And those alulae are massive. They're basically like a whole nother absolutely huge aerodynamic feather. And they get deployed during the slow flight. And that the deployment of the alula creates a vortex as well. And that vortex rolls over the back of the wing to help keep flow attached to the wing, increasing its lift while they're doing these slow, aerodynamically demanding behaviors. Typically, the more you slow down, the less force you're going to produce, and eventually you'll fall out of the sky, called stall. But with the alula deployed, you end up generating more lift than you would at that speed. And so this is an adaptation for increasing lift during slow flight, flapping flight. So these are the 2 aerodynamic mechanisms that we're going to search for in our pigeon feathers. The first one, spreading vorticity at the wingtip to reduce induced drag. And the second, delaying flow separation over the body of the wing to increase lift. The feathers that I investigated here were fairly common in pigeons and doves. Here I've got 3 different genera. All of them have this strangely shaped P10 feather, the outermost feather. So this is Eupalia, Geopalia, an Australian species, Leptotilla, New World species, Tilinopus, an Australasian species, and Turtur, which I think is African. And these feathers are found, they've evolved at least 16 times independently throughout the clade. And within Tilinopus in particular, this feather morphology has evolved at least 5 times and is sometimes different in closely related species. So this is a really intriguing feather morphology. We decided to study it in the ground, or in the diamond dove, which is a Australian species of ground dove. And to determine the function of this feather, we took whole wings that had the P10 feather, and then we also tested wings where we had experimentally molted the P10 feather. And we put those wings into a wind tunnel to simulate gliding flight, and then we put those wings on a propeller to simulate flapping flight. And we tested them at a ton of different angles of attack, and at each angle, each moment, we measured the amount of lift that the wing produced and the amount of drag that it produced. And so if we see that when a wing has a P10 feather, before that P10 feather is molted, and it produces more lift during these experiments, we might suggest that the feather is acting like the alula to delay flow separation over the wing. Alternatively, or maybe at the same time, we can see a reduction in drag, where a wing that has the P10 feather ends up producing less drag than the wing that does not have the P10 feather. And in this case, we might infer that the feather is acting like slotted wingtips to spread vorticity and induce drag. I'm going to show you some aerodynamic data. This is always intimidating, but I'm going to try and make it as easy as possible. Here, I'm directly comparing the change in that in-force production when we've removed the feather. So points that appear below 0 suggest that the wing that had the P10 feather produced more lift in this case. Points above 0 produced more lift when P10 was removed. Here, each color represents a different individual. You notice there's no real trend here. All of the points are basically equally distributed across the line. So some wings performed better. Oops, that was my live stream. Everything's falling apart. There's a phone on the ground. Does someone want to just hold that? I would like buy you a beer. I think you want the screen facing them. Screen facing the screen here. Oh, you got to turn around. Cool. Perfect. Thank you, Art. I love you so much. So no trend here with lift. We see that wings with P10 and wings without P10 did different things sometimes. But if we look at drag, we see when we're simulating gliding flights, wings that have P10 produce lower drag, which is the good thing. So the feathers, when the P10 feather was present, wings are producing much less drag than when P10 feather had been molted. This is consistent with P10 acting to spread vorticity to reduce induced drag during gliding flight. And then if we take a look at flapping flights, we see some different trends. We see that specifically at low angles of attack, 20 to 30 degrees, where flapping wing is producing max lift, we see that the P10 feathers are allowing the wing to produce more lift, much more lift than wings where P10 had been molted. Sometimes in some wings, this was the max lift that these intact wings were producing was twice that of the lift that we were seeing when P10 was missing. So this is pretty strong evidence that this feather can act as an alveolar to delay flow separation in increasing lift. On the drag side of things, we don't see any really strong trends, although it is kind of interesting to note that in those moments where intact wings are producing maximal lift, they're also producing really high drag, higher than if they had molted that feather. So this overall is pretty good evidence that this strange P10 feather in the diamond doves is acting to increase lift during slow flapping flights, but also decrease drag during cruising flights. Making these specialized aerodynamic devices, they have a specialized function for certain types of flight. And specifically, we might think of this as influencing takeoff and landing by increasing lift, increasing perhaps the efficacy of takeoff and landing, or increasing the efficiency of long-distance flight. So depending on how this feather is used, it can have multiple, multiple results here. So this is these feathers then are specialized aerodynamic devices, much like those in the tails of swallows. But you might also be wondering why I chose this example, because these feathers are also sexually selected signals. So there's some pretty strong evidence now that tail feathers initially are elongated as a naturally selected trait to increase maneuverability, but then are accentuated by sexual selection to become extra long and no longer providing that aerodynamic benefit. So it's possible that our P10 feathers in these diamond doves could also have a dual function where they're producing sonations and also acting as specialized aerodynamic devices. And we have some evidence to suggest that this might be the case because of other species like these black scoters on the top and the scissor-tailed flycatchers on the bottom, where these feathers have this weird narrowed morphology that's very similar to that we see in the pigeons and doves. I'm going to play a wing sound of the black scoter. The black scoters perform a display where they produce this really high-pitched wing sound, and then once they finish the display and they start flapping their wings harder, they actually transition to a more creaky wing sound. So you'll hear that here. A high-pitched sound. And then they start flapping faster and they change, and then the pitch changes. So sure, this is some interesting, suggests that perhaps these feathers could be functioning to produce sound as well as functioning as specialized aerodynamic devices. So we tested individual wings just like we had before, but we also tested individual feathers. And I'm not going to go through all of the data here on these, but in summary, our intact wings produce sounds about 2/3 of the time, not consistently. And those sounds never match the sounds that were produced by live birds. Similarly, when the P10 feather had been molted, we saw a reduction in how often wing sounds were produced, and also a reduction in the pitch of those wing sounds. So perhaps P10 does play a role in wing sound production, but individual P10 feathers themselves never produce sound that replicated the sounds we heard in live birds. Think back to that crested pigeon. If we took that feather off of the bird and stuck it in the wind tunnel, it would produce a pitch that's just like the ones we heard in our flapping birds. We don't see that with the P10 feathers or with the P9 feathers in the diamond dove. So this doesn't necessarily eliminate the possibility that diamond dove feathers, these P10 feathers, are influencing sound production, but I'd like to say that they're not specialized to do so, and instead are likely aerodynamic devices. Well, it can be both. So to answer this question, we've got feathers that are specialized for certain types of flights to produce lift in different ways, like in the 56 species of pigeons and doves that possess this morphology. But we also see some feathers that are adapted to produce sonations during flight. But there are also a lot of species that have that produce strange sonations but lack an obviously specialized feather. So we can have birds that have this aerodynamically stereotyped morphology, but still produce a sonation. So in one of these species I studied was the majestic city pigeon, a rock pigeon. And these birds produce wing sounds that have long been thought to be communicative, but they have relatively stereotyped feather morphologies. So I wanted to determine exactly what was going on here, how they were producing those wing sounds, and perhaps if there were maybe some structural changes to the feather that were allowing it to produce sounds, rather than general shape changes. So we closely investigated 20 wings from 10 male and 10 female rock pigeons, the outermost 5 primary feathers, which are the ones that are most often involved in the sonations. Overall, we collected about 3,000 data points. or morphometric data points, and determined that there's this one region of the outermost primary feather that actually has barbs that are extra long and they curve towards the tip, something that we don't see more proximal on the feather or more distal on the feather. So these weird curved barbs actually create a region of the feather that's really floppy. Its stiffness is very low stiffness. Floppy is a very good word for it. And we experimentally increased the stiffness of that region by applying some aerosol fixative or hairspray. And that hairspray increased the stiffness of that region, prevented those barbs from being floppy, and then we let these birds fly. So here is a spectrogram of a sound of the wing sounds of birds before hairspray. I'm going to play the sound for you, and notice that there are these nice little discrete tonal stems. Those are discrete tonal sounds produced at about 700 hertz. Here's the sound. The bird's going to fly back and forth in front of the microphone a couple times. That nice squeaky sound. All right, so we got some squeaky sounds in these plates. And then if we hairspray that region of the feather, the bird is flying back and forth in front of the microphone, and those squeaky sounds have completely disappeared. We also see that our spectrograms no longer have those tonal steps there. We can repeat this experiment in the wind tunnel. This isn't going to play either. Okay, where we can take a feather, put it in the wind tunnel, and it will flap and flutter above a certain wind speed. And when it starts to flutter, it starts to produce tones. And then we can hairspray that feather, do the same thing, and it will no longer flutter and no longer produce tones. So this is a pretty strong link between the flutter in that strange region of the outermost feather and the sound production itself. It also turns out that when P10 is fluttering, it produces significantly less aerodynamic force overall. So P9 feathers, when they start to flutter, or when we put them into the wind tunnel above this speed, they do not reduce the amount of force that they produce. Similarly, P1 feathers don't change the amount of force they produce. But for some reason, fluttering in P10 actually decreases their overall force production. So this kind of places some feathers in the middle between these morphologically deviant shapes that are really weird. But this feather doesn't necessarily have a strange shape to it, but definitely has some interesting changes to its material properties that allow it to produce tones. And those changes may actually influence its overall force production. So why the weird things? Well, sometimes we have feathers that have a specialized aerodynamic form, like the red feather. Sometimes we have feathers that are co-opted to produce sounds, like that green feather. But we also see sonation specializations that influence the feather's structural properties instead of its overall shape. And in all cases, these specializations aren't free. They do come at a cost. So for example, flapping feathers, those flutter, like in, I think they have an animation for flutter. Is it gonna flutter? Yeah. The fluttering feather actually reduces its overall aerodynamic force production. And we might also infer then that flapping in this green feather also reduces its overall aerodynamic force production. And even in our specialized aerodynamic devices, remember I pointed out that when this guy is producing its maximal lift, it's also producing more drag than it would if P10 had been molted. And so this makes it a really high-powered maneuver that some birds just don't have the energy to commit to. So overall, these morphologies are they're fairly rare among birds. In pigeons and doves, they are pretty diverse. I haven't even talked about these two here, and eventually at some point in my future, I would love to do that. And there's also some really interesting avenues of research that we could take looking at the developmental parameters that regulate the shape of these feathers, which we think are probably the same between all these feathers that have this increased and elongated barbs. So a lot of interesting things I could be doing in my future with this project. It definitely doesn't have to be over, even if my dissertation is. And with that, I'm going to go ahead and take some time to thank some people. All of this, the diamond dove research with that red P10 feather, was conducted in collaboration with Biology 403 students, a bunch of undergrad researchers who were phenomenal and helped me do a lot of mini projects over the course of 3 or 4 years, trying to figure out exactly what was going on with the sound production on these feathers and the force production of them as well. I also have to thank all of the grad students and friends in town for making grad life bearable and making this PhD possible to conduct and complete. I specifically want to thank every single one of you who tolerated me stopping and taking a photo of a bug on a trail for the 100th time in a day. I very much appreciate you indulging me. I also have to thank Chris, Natalie, Tony, Brett, and Gila for being absolutely phenomenal lab mates. Our lab has always been really supportive of each other, providing feedback on manuscripts, teaching each other new techniques, and just being engaged in each other's learning and teaching and everything. So it's been absolutely phenomenal working in this lab group. I also have to thank my committee. Doug, Eric, and Art have been extremely helpful in their feedback and being available to chat about my issues and things like that. I'm very thankful to them. I also really have to thank Chris. He has been an inspiration. He's like my scientific role model. He has challenged and guided this dissertation in ways that I never expected and has made me a much better scientist. And I really, really appreciate him for everything he's done. As well, I have to thank Peter Wimberger, who was my undergraduate advisor, and he planted the seed of this dissertation 10 years ago. And he's also the reason I went to grad school and also the primary influence in my teaching style and my passion for natural history. And so he has been a huge, huge influence on my life as a scientist as well. I'd also like to thank Brett. Brett has been an amazing advisor. He is always so patient and enthusiastic and positive, but never unrealistically so. He has been a phenomenal influence on me as a biologist. I think that Brett is possibly the most amazing experimental biologist I've ever met. Watching him tackle a problem, troubleshoot it, and collect data all in time for beers over lunch is absolutely amazing. And I'm still. And I also have to thank him for catching those pigeons in the high-reach corners of those aviaries. Thank God for him. So he has been a huge influence on me, and I'll continue to strive to excel in all of the biology I do today because of the example he has set. He's an amazing, amazing biologist. And then lastly, I have to thank my family. They have been so supportive of me being a nerd my entire life. They've nurtured my passion for science and birds in so many ways, and I just cannot express how grateful I am for never discouraging me from being the ridiculous nerdy child at 7 to pursuing an undergrad degree in biology. And even at the age of, in the 7th grade, I told them that I was going to go to grad school to get a degree in zoology or ornithology, and they've been supportive through all of it. So with that, I will take some questions, I guess. Yeah.
How much does the speed of the wind affect the frequency of the flutter? Like, you have to get it really close to what the bird is actually doing, or if you get it in a general area, the frequency is constant.
So one of the physical features of flutter is that it only initiates above a certain flow velocity. As the flow moves over the feather, it's inputting more and more energy into it until it exceeds like the elastic properties of the feather, and then it starts fluttering. So you have to get to a certain threshold, and then it'll start to flutter. But beyond that, and the way that it influences flutter and sound production is really variable. Sometimes the flutter will jump to a different mode. So you'll get like a normal sine wave, and then all of a sudden the whole feather will start twisting instead. It does something different. Sometimes with an increase in airflow, you also see an increase in the pitch of the sound, but it's not like a one-to-one increase or anything like that. Yeah.
Thank you. One of the graphs, let's see if I get that right, it was P10 that you were testing whether it affects with
Yeah.
and we have different individuals, and
Yep.
I noticed that the variation among individuals was almost as large as the variation.
A lot of variation between them.
And in pretty much every side. And what is that variation due to just the general shape of the size of the feathers, or because it seems like that particular factor that left that the swans that's the feather.
Yeah. So all of the experiments that we did with the P10 feather, specifically because it was a paired test design as well, have been really difficult to communicate effectively. Like if you average all of those, the variation disappears, and it's like not helpful. You don't see any major changes, but it's the moment-to-moment changes from 10 degrees to 20 degrees, from 20 degrees to 30 degrees in a given individual that tends to tell the story better. And so we definitely had problems talking about or trying to figure out how best to express all of that variation consistently. And so we focused on moments that are of critical importance. So like the peak lift production in flapping wings is always higher in intact wings than it is when the wing is lacking P10. And so instead of trying to tell a story about how every point is different in different ways and to try and compare the curves of these, it was too much. We decided to focus on small things, and those were consistent across all birds. So for example, in cruising, fighting flight, we see all birds always, except for maybe 3 instances in one wing, were producing less drag when their feathers were present and when P10 was lacking. And then in flapping, at all velocities and across all birds, at 20 degrees, we always saw wings were producing significantly more lift. Yeah. But yeah, it's definitely hard. I tried doing repeated measurements of ANOVAs and all kinds of things to try and quantify exactly how wings differed, but we decided to focus on the important details instead. Yeah.
Just thinking about this. So you mentioned the cost.
Mm-hmm.
How much variation is there in can you imagine how?
Yeah. That's a really good question. I think that so for sound production, the sounds themselves, the tones that feathers were producing, were they were not as variable as like the force that was being produced by wings with and without P10. So the variation in sound production was definitely less prevalent. However, I do have an interesting story about this with this blue feather here, which is one I haven't even talked about. These feathers actually vary in populations dramatically, where some have this cutout design shape, and then some have the inverse of that, where they have added a bulge. And they are populations that, at least the story goes, that they have diverged around the Himalayas and then met later, and they now have separate feather morphologies, even though we still consider them the same species. And then there's also populations that have diverged on either sides of a mountain range in Vietnam that have done the same thing. And so either there's something fairly plastic about this ability to change from one feather shape to another, because it's not just that they become like slightly less indented. we actually go from this shape to something more like this shape. So I think that there's a lot of potential avenues for studying like the transcriptomics of the feather development. We pluck a feather in an individual and watch it grow back this brand new weirdly shaped feather. In some individuals, we even see that they have more than one. They've duplicated the morphology in adjacent feathers. So there's a whole lot of really interesting things we could do to try and figure out exactly how those shapes are varying between populations, but definitely no idea at this point. Just a lot of stories. Yeah.
You said that these sounds were thought to be communicative.
Yeah.
Do you think that they are, and if so, do you have
yeah, so definitely, so because they're sonations, they are communicative. Right? The sonation is a non-vocal acoustic signal. It's just we're not really sure what they're signaling. So in the screaming feather, yeah, I don't know. I think that it's probably signaling alarm because it is intrinsically linked to wing beat frequency. So if a bird is taking off faster with more rapid wing beats, it's going to produce those buzzes, those sequences of buzzes closer together. But there's also, this one species, the one that has the largest protrusion, is also the one species that has been described as having a sexually selected flight display that involves wing sounds. So I don't really know. The only other research that's been done on pigeons and doves suggests that feather morphologies are producing alarm signals. So, I mean, we could make that inference. But all other birds, that has never been described in other species of birds. Alarm signals being produced by feathers in the wings. So we don't know. It would be fun to study, for sure.
Maybe one more question.
So with the P10, the red one, so you had all these repeated evolutions
Yeah,
over
16.
and over again across that group. Do you have a sense of time?
Yeah.
And so do you have a sense of anything about the ecology?
Yeah, so it's never been lost. Potentially been lost in one species, but we're unsure about its position in the biology. So it's possible that there is something really beneficial about gaining it, but again, it does come with the cost of producing more drag, producing effects. Sorry, say your question one more time.
Okay,
I'm
yeah,
so excited.
So why? So,
Yeah.
so from an approximate sense, or
Yeah.
but from a looks like these tiny birds have potential functions are rights, right? So why is there? Do you think it's chance and everybody would do it if they had those mutations, or do you think it's that they those which go to?
Yeah, we did do some like really rudimentary Pagel analyses comparing the discrete morphology here to like a bird being arboreal versus terrestrial. We found no strong correlations because the Phalaenopus clade has repeatedly evolved the morphology so many times, but its ancestor was arboreal. There was a signal there, but that's just because there was no repeated events. So it was like a pretty weak way to infer that. So it's possible still that there's a correlation between the ability to take off rapidly from the ground, to flee a predator. Perhaps the feather morphology is influencing birds in that way. We also tried to look at like migration behavior or a history of long distance dispersal, and all of that has been difficult to do as well. It's just been a lot of data that's not fitting into bins well and things like that. And so it's a little weird. But it's something I think we could get an answer. I don't know.
All right, let's thank Robert. And,